Now, we will switch to this backend tool. This tool is called Microvent. This is basically a CMOS layout and simulation tool, and it have a support up to 22 nanometer technology. This we call deep submicron technology, and it have support for silicon on insulator. As I already told you that silicon on insulator technology is the latest technology. We are currently working on that. So, it have support for that also. Let us start with this tool. This is the shortcut for that, Microvent. Once I click this, I will get this window. This black screen is by default p type substrate, and this is the palette. I will explain this later on. Before any kind of layout, you need to first select the technology file, and since this is based on lambda rules, so you have to set that lambda also. Like first option will be like select the foundry. These are the design rules. It have support up to 22 nanometer technology, and suppose I will select this one, and after that I will just set this lambda value, this one. What is this? This lambda is just equal to half of VDD. VDD is like 65 nanometer technology. This is for 90 nanometer technology. So, this lambda will be just half of that, 0.045 micrometer. Okay. After that, we will consider some simple layout. First, I will take one simple example like NAND gate for this, or within more simple like simple CMOS inverter. How we go for the process step in CMOS. Before that, there is one module that is called DSCS3. This is a module which is interfaced with the this tool called Microvent, and this is like a digital schematic and simulation tool. This is the library. Some basic cells are there. These are advanced. You can select any component. That is very simple, just drag and drop any one. Like suppose this is AND gate, I will provide 2 input and I want to observe the output. So, I have selected this diode, just interconnect. This is too easy, just interconnect this. After that, like this, and then you can go for simulation. Say this is AND gate 1 1, I am getting output 1, I am not getting 1 means I am getting 0 for other cases like this one. This is the clock frequency, you can vary this also. You can check out the timing diagram, like this is my input, first input, second input, and then output. So, I am getting this timing diagram. You can even create the macro, just click this one, and you can edit this one also, whatever. You can save this one, just click and then go to insert this. You can save that, and whenever for like big kind of design, like you are you want macro level designing, so you can do like this one. Now, I will tell how this have interface with this Microvent. Suppose I will select one simple example, full adder. These are already some examples in this folder. Just select that, like simple full adder. This is the schematic for full adder. You can verify this, and you can generate the timing diagram also. After that, just click this file, and then just make Verilog file, or first of all save it, like I will save it, save as, I will give the path like suppose desktop, save, then I will generate Verilog file. This is the Verilog file. This is another HDL which is very popular nowadays, and this is very easy and similar to C. Like keyword is like similarly in VHDL we write entity, then architecture, then process block, lot of things. But in this we just write the module name, input, output ports. After that, I will declare all the ports, like this is input, this is output, these are wires, these are reg. I have to define that. After that, I will just, there are various kind of modeling. So, this is switch level modeling, we call this one. After that you can even simulate this one, just copy this into the Xilinx or Ultra and you can simulate this. This is just SDL generated by itself by this tool. After that I will just close this, open this microwin. Now I will show that how this DSCH has interface with this microwin. There are two compilers, one is called compile one line, another compile Verilog file. Just click this, open that compile and back to it. This is the like layout for that full adder, little bit complex, but it is optimized one. I will explain a simple layout also. There is another compiler, like suppose this one. Suppose you have some logical expression and you want to generate your layout automatically by this compiler. So, just select any one of this, like suppose I select this one. You can edit this one also. Suppose you want something else, so you can edit that. Just click this compile, it will automatically generate that layout. So, these like tool provide very much flexibility. After like front end part, you have to go for layout. So, you have to decide from where which side you want to go for layout designing, like you want to use the compiler or you want to optimize that manually, that depend upon the designer. Okay, now I will take one simple example like how to create one simple NMOS. For NMOS you need like I will draw one diagram. This will be of substrate p type substrate. You need two and doped region for your like source and drain. After that, here there will be gate. This will be your gate. So, for simple layout of one simple NMOS, I need one substrate, some portion for source and drain, and that is diffusion, and then polysilicon for your gate. These three layers are needed. After that, I needed some wires to connect this drain to the external world. So, I need some metal layers, wires, two doped area, diffusion area, one substrate, one gate. This is the basic MOS cell. So, I will create this one. First, I need one. Since this black screen is by default p type, I have already told you. So, I have selected already the technology file, this one. You can check out 90 nanometer technology. It have support up to 6 metal layers. So, there are 6 metal layers here, and then just click this, and the area should be at least 4 by this will come at the downward, at you can see at the left part 4 by 12, this much. After that, you need some polysilicon. I will select that one, and this should be at least 2 lambda. Okay. And then you need some metal layers to show the gate and to show your like drain and source region, this one, and like this. You can check out the 2D view. This is the 2D view. This is the strain technology I have already discussed with you. Like we need to put some strain here, so that there should be there we can control the atoms, mobility of the atoms. And after that, you have put these metal layers, and now you needed some wires only. So, you need to put some contacts. So, just right click contact layer, just right click and like contact layers. These are, now you can check out again the 2D view. This is the 2D view जो जनरली हमें किताबों में मिलता है. And अब आप ये कहोगे कि हाउ वी कैन रिमेंबर ऑल द लैम्डा रूल्स. So they have given all the design rules, this one like based on like wells, diffusion, polysilicon, contact, metal wires, metal 2, metal 3, or like pads. So they have given for like just for your reference. And there is one DRC, that is design rule checker, that is online design rule checker. Suppose you have made some mistake, suppose actually this polysilicon should be 2 lambda. See this, lambda shows the distance between these two grids, and this is equal to 2 lambda. So my channel length will be equal to 2 lambda, and they have mentioned already that polysilicon should that length should be minimum 2 lambda, okay, and this width should this extension should be at least 3 lambda. Suppose you made only 2 lambda, you just click this, it will show up that error, that it should be at least 3 lambda. It can be more than 3 lambda, but at least that should be 3 lambda. So I will just click this and all, and like now you can again check out. After that, now I want to verify that whether it will work as a switch or not. So I need to put some like signal here, and I need to close this one gate, and I need to put some like visible node like to see the output. So I will click this, this is the visible node, put here, just name that, assign, take one signal, input signal, input, and you can vary the frequency also, even rise time, like fall time, high time, fall time, you can vary this one, just assign. After that, just apply VDD here, so that it will be close every time. Now go for simulation. This this part is called nano lambda. Actually after this layout, I will go for simulation. This one, this is called pro thumb. See this, I am getting this, this is my input, this is my output. What you are observing here? I am observing that I am getting weak 1 and strong 0. This is actually the limitation of the simple NMOS. This is because you need some threshold voltage to apply here, so that this channel can be created. So that is the reason actually which due to that it have drawback like weak 1. Similarly for PMOS, that weak 0 will be obtained. So we go for CMOS technology. Now now I will draw the PMOS, just for that, since this is P type. So for like PMOS, that should be like this one. You need one N type substrate, and then similarly P plus doped material, some oxide here, and then gate polysilicon. This is gate, source and drain. But since your like this screen is by default P type, so to create this N type substrate you need some N well. So what I will do here, I will just select the N well, just put here. After that I will select the P diffusion, like that should be 4 by whatever, and then I will put the polysilicon, metal 1 similarly. One thing noted here, we should this polarize this one N well. I will give the reason for that. See this is of like p type, this is n type, and this substrate is again p type. So, this will create one PNP transistor. So, there is possibility, suppose some high current is driving through here. So, maybe it will short circuit this one PNP transistor. So, it will damage the whole chip, because current will drive to the substrate. So, due to that reason we have to put some VDD here to polarize this anvil. We have to note this only, but like for big kind of design we can't go for like this. This is this comes under semi custom design. I am creating basic MOS, then basic capacitor, basic resistor, that is not possible for big design. So, I have to I need some like full custom kind of designing. So, there is one MOS generator, this one, just you have to select the like N type, P type, or double gate, whatever. Suppose I select this N type, what kind of like MOS, basic MOS you needed, like according to specification, like low leakage, there are different kind of MOSes, like high speed, high voltage, and just generate it, put here. Then ask for P type, generate all. I will now create the simple CMOS. CMOS inverter, for CMOS inverter it is needed like I made already this diagram. You need one P type, one N type, you need to common this gate, here you have to apply input, here you have to apply output, this like VDD, VSS, VDD, and when my input is low I am getting output high, and like when my input is high I will get my input low. This kind of inverting action will be there. So, for that I need to like common the gate. So, this polysilicon represent the gate. Okay. So, I will just stretch this one. Like this. After that I need to connect this common region for output. So, I will again stretch this one, and now I will apply the polarization here VDD. I have already explained this this thing. Then I will apply VDD here, then I will apply VSS here, and then I will apply the visible node here. You can rename this, and then I will apply the input signal. This is a sine wave, square wave I am applying. You can apply different waves also. If you need like there are options like resistor, diode, capacitor, already automatically you can generate bus, logo, suppose you want some logo, path, and like contact, inductor. Now, I will go for this simulation. Say this, I am getting this simulation inverting action. For 0 I am getting 1, for 1 I am getting 0. Suppose someone is interested, there are different kind of option like voltage versus voltage, voltage versus current, and like voltage versus voltage, this kind of. Say this is the average current 0.213 microampere, and like these are the spikes during the transition when both P and N type N will be opened. So, at that time there will be maximum power dissipation. So, you can check out this, these are the spikes. Then voltage versus voltage, you can check out the characteristic, this one finally transfer curve, and then this is frequency versus time, since there is only single component here, initially there is some variation, but after that the frequency component is stabilized. But you can check out the FFT analysis also. This is the maximum component you have, and you can go for discrete one also. This is the maximum frequency you are having here. You can you can go for FFT analysis for different sampling like sampling points, and you can analyze any input, output, whatever. There are a lot of data will be automatically available here. You can verify that also. After that, the final is eye diagram. Eye diagram is like you are familiar with eye diagram. Eye diagram is like it will represent the transition, like input transition low to high, high to low, and output transition high to low, low to high. So जितने आपके सिमुलेशन होंगे उतने ही रिपीटेटिव क्रॉस आपको मिलेंगे. So that is called eye diagram. See this green one is representing the input transition, and this red crossing is representing the output transition. So in between that, this will be the delay. You can check out the delay also, 0.002 nanosecond. So my propagation delay is 0.002 nanosecond for this particular inverter. Even there are a lot of issues for this simple CMOS inverter. I don't have maintained the W by L ratio. That is very important factor. You can check out this is the average power dissipation, 7.728 microwatt. So automatically all the data will be generated here, and you have to just analyze that one. And now I have to maintain this W by L ratio. You all are familiar why to maintain this W by L ratio. Why we are maintaining this W by L ratio? W by L ratio means since this p type like substrate have mobility of hole very less compared to this one electron. So we have to maintain these mobility of hole and electron, so that proper transition can be obtained at the output. So that is the reason I have to maintain W by L ratio. So I think there may be some examples regarding that. These are automatically some examples they have already provided. These are basic examples actually, like let's have some simple gate gate like NAND gate, NOR gate, and like some oscillator, Smith trigger, like differential amplifier, which is very important things like current mirror. So I will go for some gate. See this is the NAND gate. It is looking little bit complex because it is actually optimized one. I will made one simple one through like semi custom design, but first I will explain the layout for CMOS layout. That will be like you need these are two NMOS in series and these two PMOS are in parallel. So I have to just common this one and this one. Okay, this will be my input A, this will be my input B, and from this common region I will take the output. So I will check out the truth table also. So we have to like just make parallel PMOS and one series NMOS. So for that there is option like this generate NMOS, how many number you want, like 2, generate this one. This is 2 NMOS. We can't say these are in parallel or series, but these two are in, and after connection we can decide these are in parallel or series. I have just generated this one. These are I will generate this PMOS simply. After that, I need these two in parallel. So, how to make these in parallel? One thing is like simple way, like just increase this metal and this one, and like simply like this, and apply the VDD here, and now you need to connect this one here. So, just extend this one like this. I am just redrawing that circuit only, just I made these common, and after that this common region, here I have applied VDD, here I have taken the common connection. After that I have connected to the source of this one, simple NMOS. So, here I have connected this here. After that I will apply the VSS here, okay, and this is now it become in parallel, in series, you can check out, and this is in parallel, okay sir. Now, there is another approach, you can use different metal layers, like suppose I will delete this one. I will do one thing, I will put another metal layer, suppose metal 2 layer over this one. These are two different metal layer, have different property, electrical property. You can check out that. See the 2D view. This is the metal 2, this is the metal 1. So, there is you need some wire. So, what will you do? Just you will interconnect this one, you do not need this connection, you need this connection. So, you will just connect this one and this one. So, I will put connection here, connect layer, and here connect layer. Now, you can again check out the 2dB, say this. So, this is another approach to interconnect these. Now, this is optimized, there is no wastage of that much area. I have connected like this one, that is not needed. So, that is very simple. Now, I will apply VDD here for polarization, VDD here, and VSS I have already applied. I need to connect this one now, because I have to make common these gate. So, I will just select this one, either you can select from here or you can just stretch that one like this. But there will be definitely lot of error here, because I have not maintained that lambda design rule. So, definitely there will be some error. I have connected this. Now, I will apply the signal input here, like suppose this one here, A, I will apply here like B, and here I want output. So, either you can put even load, you can select the capacitor from here, and you can select the like capacitive value assign, and even you can select like there are a lot of math function. Say this one, these are different math function, you can apply this as an input, and even you can apply this pulse width PWL. You can give any sequence like 1 1 1 0 0 1 0, any kind of sequence, and this is ground variables. You can apply the sine wave, pulse, clock. There is a lot of flexibility according to your requirement, you just create it. See this one is unoptimized actually, and this is the optimized one without error, and I have used here metal layers. The approach, this approach is not actually good. I have to put more and more context, and I have to use I can use different kind of metal layers. So, see this, here they have connected here, and then here they have put another connection for metal 2 layers, and now I will delete this one, simulate this one. See this, now you can like verify whatever you want, जो भी आपके सारे input possibilities हैं, you can verify that one. You can check out the power dissipation values, and like I will close this one. Now for this they have provided one that is called spice netlist support. You can select PSpice or WinSpice. I think you all are familiar with PSpice and this one. This is worldwide acceptable simulation tool. We mostly use this kind of tool, or in like most of the industry you can apply. They are using now HSpice for actually practical purpose, but PSpice like it is very popular in educational world. You can just select that one, OK, and PSpice extract. See this is the code. You can import this one there in PSpice, and you can go for like transient analysis, DC sweep, AC sweep, whatever analysis, Monte Carlo analysis, you can go for there also, because no designer rely on one single software. You have to simulate in different kind of with the help of different kind of algorithm. So there is some that kind of flexibility here. And another thing that is we call CIF layout. This CIF layout is like this is the file we have to send to the foundry. Actually these are like geometric location of your basic MOS, different kind of mask, metal layers, this one. So just create this and send this to the foundry. After that this file will be read by those specific tools, and that is under wafer stage we call that, and like this is chip, and that tool will read this file, that is properly controlled, means totally controlled by computers, and that all the mask will be generated on that chip. After that we will go for proper kind of like routing and placing. So this is the method actually. Even there is one thing, you can insert layout. Suppose there is like big kind of design, so you need to add different modules. Just partition that, just create one module, then save that, again create second module. In this way create all the complete project, and after that insert layout, this option, and whatever like this one, just insert this, and another again you insert something like you can insert inverter like this, and then there is like some algorithm for optimization, for interconnecting, and then we have to follow that one, new one. Now finally I will show an example new. say this. Finally, like this is my I have already like selected this chip area, this much, and these much of pad input output pad, and this is my optimize simple full adder. Okay, you can zoom it, say this. So now you can imagine that this is not possible like manually, you need some help of software, proper kind of simulation, proper kind of like optimization. Finally, means you can decide that okay, now my chip will work, and definitely I have covered each and every like parameters. Then finally, I will generate the CIF file for this one, and I will send to the foundry. Then the headache will be there. They will within like few week they will send your chip. So for but that process is too costly. So we have to take care a lot. There is a lot of analysis, like I will explain this one actually, like interconnect analysis. This is like, suppose I have these two buses in my design, like you can imagine the PCB, like there are two interconnects. I have maintained this width, this is by default, you can edit that one, like this, apply, and after you can edit height, thickness, everything according to your requirement, and after that you can select the copper or aluminum. Still we are using these two metal layer for interconnection. After that I will ask for compute field. Say this means the expert designer can like analyze properly that what should be this like electromagnetic effect, and he can analyze like there will be automatically generated data like all the capacitance and inductance resistance value here. So after analysis we will finally like go for this kind of interconnects, like proper analysis of that interconnect. Okay, this will not now create the crosstalk effect. Crosstalk is like that is interference, it will like interface with other signals. So definitely there may be some difficulty. So this proper analysis should be there. There are different kind of like analysis, they have provided a lot of option here. And there are different kind of like we go for resonant frequency analysis and then parametric analysis, then global crosstalk evaluation, it will give all the data, like open any examples like full adder mass global, say this is the data at every node, you can check out that one, and there is other values also, and there is like different kind of analysis, global delay evaluation, you can even analyze the delay. Say this will be the delay for like whatever the component XOR gate from this node to this node, this will be the delay, and all information will be provided automatically. So after like a proper analysis you have to like then decide that what to edit and how to like obtain the specification, which I have already decided in the beginning. So these are the methods. You can check out the area also, just click this and like how much area it will take. Say this will be the area required for this one, simple full adder. And there are a lot of things like you can go for. I will take one simple example. Like this one. No. This one, and I will check out the 3D view for this one, and say this. You can like practically analyze that this will be my final block, like side view, top view, and like all kind of information will be here. You can obtain that one, and there are a lot of option for sensitivity, light position. This is just like to give the overview, like how my chip will look like particularly. And you can go for like this one is 3D view. We call this one as virtuoso fab. These are all the steps which is needed to design this simple adder, simple inverter. Actually, I have taken the inverter example. After polysilicon deposit, N plus implant, P plus implant, it will leave the step which is not required actually. So, this will give the complete 3D view for your design. This is actually simple one. So, for complex one you need to have that kind of analysis also, 3D view. And there are different kind of simulation, like you can open any kind of these one window and or using models. I have already explained this level 1, level 3 and PCM 4 models. These are different models according to the parameter, like BCM 4 is the advanced model, it contains 300 parameters. But for this one there is one module Pro Tutor, they have even provided those parameter. You can edit that parameter, you can check out the effect on that characteristic curves. So, in this way you can simulate using whatever model you want. The simulation on layout, I will take one example for this one. With crosstalk, you can analyze without crosstalk and with crosstalk, means this is the interference effect. So, you have to analyze both things, and you have to take that worst case for that one. Simulation parameter. Okay, now I will take some memory element examples. I will go for there are various example, like you can design FPGA, your like counters, your like all kind of memories, power amplifiers, multiplier, multiplexer. These all basic layout they have already given. And suppose I will select this memory one, dynamic RAM. It have support for all kind of EEPROM, like your ROM, static RAM and dynamic RAM. And I will generate one simple cell. You can check out the 2D view for this one. See the 2D view, and there are different options provided here for creating that kind of memories. You can duplicate this one also, like see this is the basic DRAM cell, and see this is the floating gate here. I have to like I want 8 by 8 matrix for this memory element. So, there are automatically they have given the option like duplicate XYZ. Just select this one like 8 by 8. Now, you can assign the value what data you want in the memory, binary digits. Just double click 1010 format, or you can go for like hexadecimal data. It will automatically convert that into binary. After that, generate. Now, it is generated, and after that according to your requirement just utilize that memory and just optimize that according to the area constraint. This much area it is consuming. So, you have to manage properly that I want this capacity memory, and how I can optimize this one. So, there are different processes for that one also. I will show one example like this one read. I have written some data here, you can check out this there is salicylate layer here, you can see this, there is nothing here salicylate. So, this will represent 1 0 1 0, here I have given 0 1 0 1. So, I have like stored some data here in this memory element. You can check out the 2D view for this one, say this 1 0 1 0. So, after that, suppose you want to delete this data, since this is EEPROM based memory. So, you want to erase this. So, there is option you can erase and you can again like dump the binary code here. So, simulate just UV exposure. So, it cover like lot of parts from embedded also. You can go for embedded kind of designing also. Okay, it will take some time and this data will be generated. You can read out that. Okay, see this, now all the data is erased. Now, you have to select proper like word line, proper bit line. After that, you can dump the binary code. Now, all are zeros. So, these are simple like memory kind of designing, that is called MEMSIM. This module is called MEMSIM, and actually this is very simple one I have described, but little too difficult to like manage and to optimize that memory elements. So, it need a lot of time. You can even like I will take some other examples like see this, they have given example related to soy technology also. You can go for that also, and amplifier. I will take one simple amplifier, differential amplifier, NP, this one. This is a simple differential amplifier that is based on actually current mirror. Actually, what is current mirror? I will explain that one first. You all are familiar with current mirror, that is just copying the current. Actually, current mirror is the concept to copy the current of your like there is one master, another slave. So, it will copy the master current. You can even like multiply the current, you can even divide the current. So, it gives the flexibility to the user, like they have provided this current mirror. Not the say this is the current mirror. So, this one is your like simple NMOS, this is another NMOS. I have just made common this one. I have applied here the reference voltage, and this is you can vary this voltage and just VSS. So, that is very simple, like I will explain it little bit, because this is very important like fundamentals required for analog kind of designing or any kind of amplifier. I need one NMOS, one another NMOS, this one. I will make this common. After that, this one. So, here I will apply, this is a master, this one is master, this one is slave, and I will make this one as like common, this one. Here I will apply some voltage V reference, and here I will apply some V like any variable. So, the fundamental is that it will like copy that much current, whatever here is the current flowing, it will be copied here. Like this concept is like utilized in differential amplifier. For differential amplifier, you need to connect like this can be based on PMOS type also. This is based on NMOS. If you have PMOS, so you have to just create PMOS like this. and just common this one, and there you required one NMOS, just ground this one, and then you required another one, ground this one. Here I will apply some load. This is simple differential amplifier. Here I will apply V reference, this is the master, and here I will apply the V vary. I will explain this one because this will be better. Suppose I have applied here voltage V, and here I have applied again the voltage V. So, suppose my current is driving from here is like I, then same current will be copied here. Okay. Here I will get the current I. So, definitely that current will flow like here, all the current will be sync. But suppose I just increase the voltage by V plus dV. What the principle of this like differential amplifier, it will like amplify the difference. Okay. I have applied V plus dV and here only V. So, the difference is dV. So, now my current will be I plus dI. Okay. Same current will be copied here, I plus dI. But since I have applied V voltage here, so driving capability of this NMOS is only I. So, that I current will be flow here, but the remaining delta I will be, I can get this thing at output. So, this can be amplified. So, this is the differential amplifier concept. Current mirror, using current mirror I have like utilized that dI current to charge that capacitor load. So, based on this one I have created this one, you can check out this, that is simple, like in initial stage it is looking too difficult, but you can see this, these are two PMOS. Okay. I have made this common. After that I have made this, there are two PMOS, okay, similar circuit, but the difference is that this one is optimized, these are made by expert people. Okay, but otherwise you can make simply like create two PMOS and MOS, common that. So, definitely you will get the result, but that is not optimized. Here the designer use metal two layer also, and a proper kind of interconnects and lot of things, many interconnect, he put many interconnects. So, I will take one, there is one option for this one, there is one option that is called simulation on layout. See this, anyone can say that what is these colors actually. When we apply some node voltage, see this is the color roadmap, it will represent this voltage, this one, this red will represent this. So, I have applied the node voltage N2, and one is like here I am getting 22 microampere current, I want to copy this one here. So, exact current will be copy if the property of this NMOS and this NMOS is practically same, but that is not possible, actually practically not possible. So, that will be like approximately equal to this one. And one thing about this one is like whatever reference voltage you have, this one, this is 0.60. So, in this region, linear region, my current will be copied, you can check out that. See this, simulate, and then simulation on layout, select the node voltage at N2, after that simulate this one, see this at this 0.60, this is the reference voltage applied at master. So, here my current will copy and it will take some time to for stabilization. So, definitely it will be approximately to this. Suppose anybody want like to use this current mirror as a multiplier. So, what he have to do? He have to just double this one, that is very simple, that current will be just double. Suppose he want to divide that. So, he have to maintain the width of this one half compared to this one. So, the flexibility with this current mirror is that suppose you want to multiply the current or divide the current. So, this will be very useful method for like layout kind of designing. So, I have explained the principle of differential amplifier, why we are using current mirrors, and now I will take some other examples. This one DAC by partitioning, just partition किया, then I just insert that proper optimization करके finally I get this one. So, this is the way to like create some basic models, and there are analysis. One analysis is called parametric analysis. I will show that this one, just double click this. This analysis, like similarly Monte Carlo analysis, statistical analysis, you can give the like number of statistic values, like suppose you want 10 values, for 10 time you want the output temperature, you just vary the temperature, give the step size, and these are different kind of analysis possible here. You just analyze, suppose you want to know the dissipation of this circuit, just this and start analysis. So, it will give that kind of characteristic curves. Voltage, just select the node voltage where you want that power dissipation. Suppose I want at this node, just select that, give the step size, give the voltage variation, select whatever you want and just analyze. So, this kind of capacitive, parasitic capacitance analysis, voltage analysis, temperature analysis, Monte Carlo analysis, you can do with the help of this parasitic capacitance. Okay. And it will after analysis it will give that data array. And there is one module that is actually for university addition, like to give the exposure to the student, like what are basic MOS models and what are the different characteristic, and how the different parameter affect the characteristic. This is the this is called pro tutor. I will just little bit. Okay, I will select the different kind of this W by L ratio, different kind of NMOS with W and L value. You can edit this one. Select the VG voltage and VD voltage, whatever. Select the NMOS or PMOS, what you want. Suppose I want NMOS, and then just it will which model you want, level 1, level 3, BSIM 4. Suppose I want BSIM 4 model. These are the different parameters. You just edit this and you can check out the effect. And like see this is the threshold of VTHO, K1, K2, thickness of oxide, like lot of parameters. Suppose I edit this one 0.3. See this, now it affect like this one, my characteristic curves. These are the various characteristic curves. You can check out the parasitic capacitance value, CGS, CGD relationship, like threshold voltage, log ID versus VG, ID versus VG, and this one ID versus VD. And there is one thing, close this one. There is some ST microelectronic support for this, and they have provided there some foundry files. You can compare that one with your characteristic curve. Suppose I have selected this one, and I will go for this add measure back, and I will go to examples like miscellaneous, not this one. There are some files they have provided already. I have to check out. I think that must be an example. We see it. I have to check out that actually those file are there, and you just open that, and it will like open the characteristic curve for that file. So, you can compare that, like this is the by default value, but you can edit that one, and you can edit, and you can like compare that one and this one, like this flexibility is given provided, like these are the latest file which already we have fabricated. So, this module is called Pro Tutor. There are a lot of things here to explain. Even you can check out the like I will take first some example. Suppose I will take one, no, this one. These analysis are like you can find out the floating nodes, because this is like big design. So, there is possibility of some error. So, it will like analyze the floating nodes, because it will create a great problem for you. You have to analyze that floating nodes also, and resonant frequency, this kind of things, and like there are different kind of like there is navigator window. Just actually double click this. See this, all the data will be provided here, all kind of resistance, diffusion, delays, capacitance value, VDD, this will be and you can check out the like interconnects also, like see this for this layer, these are the different interconnects, these layer are connected. So, in this there are different kind of analysis. After like complete satisfaction, you will finally generate the CIF file. Okay. CIF file generate, save this, and just export this to the foundry. So, finally, you will get your own chip. So, this is the actually in short I have explained this one, but it need a lot time to explain like in deep all the things. So, this is the basic one, and it you can even interface with it, have that flexibility. You can interface with PSpice, you can, it will generate Verilog code, you can interface with the front end part, like you can just copy that code and verify that one, simulate that one. So, definitely this is very user friendly and intuitive tool. So, and very helpful for student, no need to concentrate on tool, even you can learn this tool easily after a practice of 1 week, that is more than enough, I think. After that you can like concentrate on your design. So, that is the best part of this tool. There are a lot of competitor for this one. So, but it has support for sub deep micron technology up to 22 nanometer technology, you can go for that, or SOI technology, you can go for that. So, definitely it is like I can say best tool for like at least for university addition, and industry they are using. We have collaboration with ST Microelectronics and like different kind of foundries in France and in lot of other countries. So, in industry world even this tool is very popular. So, this is all about the layout and simulation tool. Thank you.